Afternoon, sir.
Yeah, I'm going to first let me apologize for the hiccups last week. Just getting the knack of this thing. So as we go along and learn, you bear with me, okay? The next thing I'm going to ask you is that when I'm here talking and I'm not hearing any sound, any feedback, believe you me, it's lonely. So I've got to ask you to ask a question even when you don't want to ask it. Say something, right?
Yes,
Now,
sir.
hear
Yes,
me,
sir.
man?
Yes, sir.
All right, cool.
Sir,
Yes.
more time it take a time for us to answer. So like you asked, you hear me, man? It might take a couple of seconds before you get the reply. So you have to wait a few seconds at time, yeah?
Okay, great. Thanks. All right. Dre, you there, Dre?
Yes, sir.
Can you turn on where the name will come up when somebody talking, so I can see who is talking? Is that possible?
Hold on, sir. Hold on.
Yes, like that. Okay. All right. Okay, so we're gonna go back from vector field, okay? Nobody not hear me, man.
Yes, sir. Yes, sir. We hear you,
Yes, sir.
man.
Yes, sir. Yes, sir. Yes, sir.
Okay. So and next thing, can you guys record the screen? Is it possible? Or Dre is gonna record it and send it to you guys. I don't know.
Yes, sir. It is being recorded. At the end of this the meeting, I think I would get a recording file and just send it same time.
Yeah,
Okay.
then the meeting
Or
it should
whoever
come
want
to.
to take.
So what you want to do with the recording file?
Well, who
Yes,
wants to
sir.
do with the recorded file? Me?
No, as it
No, sir.
as in the
I
person
think he's
recording.
saying that whenever the recording is done,
Yeah.
Yes.
you get the option to share it.
All
Yes.
right. So you know, share it with the class.
Yes, sir.
As far as the fundamentals is concerned, that is the vector algebra and the vector calculus, I'm going to talk from these notes. When we actually get into the electromagnetic fields, where we're going to do the electric field and the magnetic field, I'm going to use some PowerPoints. Okay, so maybe by next week we'll start using the PowerPoints. Right? All right. So vector field. I mean, that's kind of self-explanatory, like gravity, right? Gravitational force. So if you have a stone in the atmosphere, it is pulled down by gravity. Gravity pulling it to the center of the earth. So that's a vector, right? So what we would refer to as a vector field would be the complete atmosphere where there is a pull towards the center of the earth by gravity, right? So that's referred to as a vector field. Here in the last paragraph there I have some other examples of vector field, like velocity of particles in a moving fluid, wind velocity in the atmosphere, voltage gradient in a cable, displacement of a flying bird in the space, etc., etc. Now, how do we represent vector field? Let's start with the very basic in 2 dimensions. We have a vector. If you look at figure 1, with a starting point at O and a terminating point at A. So the vector is from O to A, right? Now, we usually represent a vector from O to A, like you see here. You see the arrow? You see,
Yes,
you see where I'm pointing the arrow?
Yes, sir.
Yes, sir.
All right, so a vector start from O and terminate at A, and we put a bar over it like this. So the vector is OA, right? Or the OA have a dimension of R. So OA equal R. Important to say that you will see if you look in some of the reference books, instead of a straight line here, you might see a wiggly line over it like this, right?
Yes.
So you must look out for that. So OA is R. Now, this is a big deal. The unit vector. If you, in a scalar system like the number system, you count by units of 1. 1, 2, 3, 4, all the way up to 1,000,000, right? So the unit for a scalar is 1. Similarly, in vectors, you have what we call a unit vector. So remember vector OA here. So whatever that unit vector is, it's R times the unit vector. Just like 10 is 10 times 1. You with me?
Yes, sir.
Yes, sir.
Okay. So the unit vector is R times whatever that vector unit is. Now, we represent the unit vector with a small letter, in this case A, with the vector sign over it. And we have OA here showing that the unit vector is in the same direction as the vector going from O to A. As we go along, we are going to be able to drop this OA. So for example, if we have a vector going from 0 to 10x, right, we would say 10x in the ax direction. All right? Now, if just like in the scalar system, if a vector is known, let me turn this off. Yes, Miss Dunkley, I'm in class. No, man, I'm in class, but I set up a new account, so it's sent to their group email, the link. So the link, everybody should know their group. No, it's not the same one. Dre, give me that ID again. Let me give Miss Dunkley because some people are having problem.
Repeat that, sir.
Huh?
Repeat that, sir.
Oh, okay. Look for a WhatsApp from Dre Morrison. Okay. All right, Jay.
Yes, sir.
All right, take Miss Dunkley WhatsApp number and WhatsApp that link to her.
Okay, sir.
Her number is 376-4246.
Okay, sir.
All right. All right, guys. Let's give those guys a couple of minutes to join us. So far, any questions?
Not as yet, sir.
Huh?
Not yet, sir.
Oh.
Sir,
Yes.
have you decided on any waiting for the entire course, like assignments and so forth?
Yes, I'm going to give you some assignment. The way I'm going to do the exam is gonna be sort of multiple choice, but everybody is gonna get a different question and get a time to do it. Right? So say for example, it's 12 multiple choice, right? And it would be 5 minutes per question. So I'm having them set up the system where everybody will get a first question, but you won't get the same question that I get. Right? And it would be, to get to the answer, it would be a short workout, right? You wouldn't get anything as involved as what you would get in a question that would require 30 minutes, right? You'd get a question one that require a 5-minute working. After 5 minutes, you make your choice based on what you work out, and you can't go back to that. You understand?
Okay, sir.
So that
Can you
would be
repeat that, sir?
All right. Say you're gonna get 12 questions, right? So each question I'm going to say says a 1 hour test, right? So each question would take 5 minutes then, right? 5, 12, 60, right? So everybody will get a question. But no two people will get the same question. At some other point, maybe the question that person 30 get for question 1, maybe that's question 2 for person number 1. But by the time you get to that, you would be locked out of question 1. So you couldn't call, somebody couldn't tell you the answer for question 2. May that make sense?
Sir,
Am I making sense?
So sir.
Sir, the issue that we would have had with that would have been internet, because the internet is not that stable. So whereas it would have been timed and all of that.
I have a question, sir.
Wait, sir, the class marker platform them using?
Huh?
They're using the class marker platform?
I think so, yeah.
I think
Sir.
that have the capability to pause when someone's internet bugs out, so the timer should pause.
Sir,
Okay, yeah.
so you're saying in essence that we can't go back.
No, I don't think you will not be able to go back. So
Okay.
I wouldn't be able to ask you what question did you have. Say I ask a vector question, all right?
Mm-hmm.
You couldn't, when you reach to your vector question, you won't be able to call your brethren and say, what was the answer for the vector question?
Get where I say, sir.
Eh?
Get you know, sir.
So, and the only good thing, the good thing about that, as far as I understand, is that when you finish the exam, it give you your grade.
Sir.
So that good for me, because when I have to go back.
So sir.
Oh,
Sir, is it
yeah.
a case where we will see all the questions at once, or you only be getting one question at a time?
I still getting up to speed on it as well. So I'm not quite up to speed, but my understanding, you just get one question.
So another question, as it relates to the, all right, that is for the exam, you say, right?
Yeah.
That would value like how much? What weighting does that carry?
Then send out something where they said that we can we must send in how we're gonna weight the thing, right? Normally they would go by the syllabus as how it is. I believe it's now 10, 30, 60 or something like that. But I mean, I think with this situation now, I have the flexibility to do what I want to do. So we can decide. You know, you can tell me what you're comfortable with. I may deal with it.
Sir, based on the situation, it would probably be easier. Well, just a suggestion based on some of the modules that were done before, would be easier to increase the coursework, and the finals would be 30%, and everything else be 70.
Increase the.
That's a suggestion. Yeah. So the coursework would have worth 70%, and then the final exam worth 30.
Yeah, I mean we can are close to that. I can do that. I think we can do that. But when we get to work, we don't have to do it to the man. We don't have to do the make it be an individual thing, but have the community thing, you know. Because the objective at the end of the day is that you learn the material. So I have no problem giving you increase in the weight of the coursework. But you know, I just hope at least the majority of you guys try really to do it and learn it, and you know, instead of just Xerox a thing.
Question.
Yeah.
Dre, I understand that you're the host. What is the protocol when is this gonna end in 40 minutes or going on?
You mean this?
It's supposed to end in a 40 minutes, but when it done, you'll just use back the same link.
Same link. All right.
Yeah.
All right.
All right. Do you have some other people come on now?
Yes, sir.
Okay.
So
All
far,
right.
you have 28 students, sir.
28?
29.
Okay. All right.
28, I must have sir night.
Okay. All right, we're getting there. All right, so I'm going to continue. So that is that for the vector. Now, vector algebra. Just like in scalar, you can, if you have a vector, you can scale it. You can add two vectors, or you can subtract one vector from the other. How you scale a vector? Okay. Say you have a vector A. You can make that vector A 10 times, right? So you can have a multiplier, alpha. So alpha times vector A, as an example, 10 times vector A, where alpha is greater than 1. Now, if alpha is a fraction, that means you are going to divide A by some number, or multiplying A by the fraction, right? So alpha is less than 1. Your result is a shorter vector. If alpha is greater than 1, your result is a longer vector. If alpha equal -1, means that you change direction. So instead of going from O to A, like before, now we're going from A to O for alpha equal -1. How you add two vectors? Here you have a vector A going from O to A. and a vector B going from O to B. This is really what happened now. If you go back here, you're going O to A, right? So if you move vector B to the end of vector A, so O to A would be going this way, and you move this and bring it up here. So O to B would be going from here to there. It's like going from the engineering building over to the admin building, right? If you walk in a straight line from one of the classrooms on the first floor there, and you go to the back under the tree, and then you go along some part over to the admin building, or if you go through the door, no, say you go down the hallway to one of the door and then go across to the admin building. Those are two separate vectors that get you the same place, right? So in this case, I have a vector A going this way, so I go O to A and O to B. So how you do this geometrically? In this case, what they did here is they go along B first, here, and then you go along A. You with me?
Yes, sir.
So vector A plus B would be from O to A. Okay. So vector A plus vector B would give you vector C. All right. So remember, I started out here saying by moving vector B up here and here, what we did was move vector A. So vector C is vector A plus B, or is the same thing as vector B plus vector A. So essentially what we do is what we call a parallelogram rule, where we just complete the parallelogram and the resultant is the diagonal here. Okay. You can have more than two vectors, of course. All right. Here we have a total of 4 vectors. We can add all 4 of them. In the same way as we can add 2 pounds of flour, 6 pounds of flour, 3 pounds of flour, 1 pound of flour. We have 4 vectors. How we add them? And again, you can start with anyone. Right? We start with A. So we go O to A, right? And then B, which is in this direction. So we have the magnitude and we have the direction. So at the end of this, you start with B and you go along that direction. And then vector C, you go along that direction. And vector D, you go along that direction. And the resultant vector R would be where you start to where you end in that direction, from the starting to the end. That's your resultant. All right. Now some rules. And I'm sure you guys have seen all these rules before, right?
Yes, sir.
You know
Yes,
the
sir.
commutative law. A plus B is equal to B plus A. That's addition. So vector A plus B is equal to vector B plus vector A. Multiplication by a scalar, alpha times A equal A times alpha. The associative law, now, as you know, if you have this bracket here, you complete what's in the bracket first, right? So if you get this with some simple algebraic function, you do this first and then add A to it, right? For addition, the associative law, vector A plus B plus C, parenthesis, equal A plus B, parenthesis, plus C. And if you are multiplying by 2 scalar, beta times alpha A is the same thing as beta times alpha times A. In other words, 10 times 6A is the same thing as 10 times 6A. The distributive law for addition, alpha times A plus alpha is the same thing as alpha A plus alpha B. And for multiplication, alpha plus beta times vector A is the same thing as alpha times A plus beta times A. Cool so far?
Yes, sir.
All right. Can't impress upon you enough that the electromagnetics material is very, very easy. But if you miss these nuts and bolts, that's what makes the thing difficult. So up front here, I ask you guys to spend some time and understand what we're doing when we're dealing with this. Okay, subtraction of a vector. Again, we go back to what we did when we add two vectors together. So vector A minus B, A and B, is the same thing as vector A plus negative B, negative vector B. So vector B, or negative vector B, is if B goes from O along this direction, negative B goes from O in the opposite direction. So you complete your parallelogram with negative vector B and vector A, and you get vector C. So C, this is A minus B. Okay. This is self-explanatory. Identical vector. If A minus B equals 0, then vector A is equal to vector B. Okay. Now, coordinate systems. I think last week or Tuesday, I mentioned to you that there are countless amount of coordinate systems. Because just to name a few, you have elliptical, you have triangular, you name it, it exists. But for our intent and purpose, we are going to only deal with the three basic ones. Cartesian is the same thing as rectangular. So if you have a room, which is a rectangular room, going along one wall, if you call that X, going along the other wall, you call that Y, and going from the floor to the ceiling, you call that Z, right? No. A lot of problems, a lot of complex problems. I remember seeing some students when I was at university, and those guys were doing like the PhDs in electromagnetics. They would be, say they are using the Cartesian coordinate to solve problems, to increase the precision of the result or the accuracy. They would require more than 3 coordinate systems. For example, in the Cartesian system. So you would see, say, someone solving a problem with x, a coordinate called x, one called x0, x1, x that, y0, z0, z3, z, you know? So, I mean, the point I'm trying to make, you can have infinite amount of coordinates in any one of the systems. But again, for our purposes, we are only going to deal with how many?
3.
Huh?
3.
Okay.
Yes, sir. The more you have, the more accurate the vector representation or something.
Right. Right. So, say for example, when you get your big job, a design missile for touch jump. you know, you know, you not go want you not go want it come, you know want it lick me. You understand? So we down the road from the White House. You don't want to touch me, right?
That's precise.
So you have a precise. So maybe you have step up your coordinates to 20 or and use your computer for modeling. Or another example, say for example, you see, I'm going to talk a little bit about this. All right, so you want to, so them equipment where them guys make for clear your artery, when you have black artery, or them something, and, and you guide the wave down the what do you call it now? You guide the wave down the artery, right? So you don't want it run off and bore up the artery, the side of the artery, because so I know they don't do so, you know that. So you want it go accurately down, be guided accurately down the thing. Or if you have burn a cancer cell, burn the liver when you go after the lungs. You with me?
Yes, sir.
So the 3 system again, we have the Cartesian or rectangular coordinate system. We have the cylindrical coordinate system and the spherical coordinate system. These are the 3 that we will focus on. Now, I'm sure you guys have your soft copy of the reference books where the syllabus. At this point, I'm not going to assign any particular problem for you to practice from these, but I advise you to do some work on trying to solve some of these examples on coordinate system. So let's discuss the first one, which is the Cartesian. Okay. Cartesian. A rectangle. Your origin is here. This is your x direction. That's along one of the walls that we talk about. The y is there along the other wall on the floor. And the z is there. Now, the right hand system is x rotating into y. And the left hand system is the x rotated. Oh, let's go. Okay. Think of it like the right hand screw, right? So you're going to rotate this way. With the left hand screw, you're rotating this way. So x rotating into y this way. So for the left hand, this would be x here. This would be y here. All right? Which for the right hand, where you have your y would be your x, and vice versa for the y. Still in class. Okay. The planes. Planes, let's go back here now. You have three planes, right? You have what we call the x equals 0 plane. So again, when we start the real stuff, I'm going to say, well, I will see problems like an electric field is along the x equals 0 plane. That means x equals 0. So the only quantity on that field would be y and z, right? Because it's along the x equals 0 plane. So it's along this side, either this side or the back side. If we say it's on the y equals 0 plane, you're on the xz because it's on this plane. It's either here, you with me? Or here.
Yes, sir.
Yes, sir.
If it's on the z equals 0 plane, it's either at the bottom here on the floor or on the ceiling. So z equals 0, this plane or this plane. X equals 0. No, I think I'm saying something wrong. If it's on the x equals 0 plane, it's on this back side, right? Or it can be on the x equal 6 plane, where It's here. So it's on this front side, but it is 6 away from 0.
Why 6?
I'm just giving that an example. Say, okay.
Oh.
All right. If it say the statement is on the, you will either say it's on the XY plane then, right?
Mm-hmm.
It's on the XY plane. So it's either on the back side here, right? Or on the front side here. But it lies, no. It's on the XY plane. So it's either the bottom, the floor, X, Y, or the ceiling, right?
Yes, sir.
You with me?
Yes, sir.
If it's on the XZ plane, it's either on this side or on this side. All right? Noting, and similar, if it's on the YZ plane, it's either over here or in front here. But if I say it's on the X equal 0 plane, that means it's on the XY, but you begin at the origin. So it's on one wall there, right? That makes sense?
Yeah, man, only the back wall.
Right. But if I say no, it's on the, if on the X equal 4 plane, it's on the YZ plane, but it's here, from here, right? Where X equal 4. You with me?
Yes, sir.
Which is very, very key, because that's how they state a lot of the problem. It's on the X equal 4 plane, right? Or Y equal 6 plane. That means you would be out here. Cool?
Yes, sir.
Okay. So here they said X equals 0 plane, it would be YZ plane, right? Just like what I was saying up there. Okay then. Point in the rectangular coordinate system. So here you have the system, X, Y, Z. You have a point right out here. So you have a point at, in this case, at one corner of your rectangular system. So what you have done, you travel, say the point Q is X1, Y1, Z1. The example here is Q is at 3, -1, 2. So let's go here now. So here is your point P. So just like when we have the vector, right? For that we started out with in 2 dimension. Here in 3 dimension, vector is P at this point. That means you travel x1, and then you travel y1, and then you travel z1. For the example that we look at, point P is at 3x, -1y, 2z. So then here is your origin. You travel along your x 3 units, along your y -1, so it's -1y, and along your z you go 2. Notice something here now. 3x -1, 2. Right? You visualize that properly?
Yes, sir. I see.
Yes, sir.
Oi.
What if you had label your x and y interchangeable, like put x where y is and y where x is? Could you have done that?
Yeah, man, you can do that, but you have now. May I advise you. You see, customarily, it's represented this way. You will come to the same point, right? But you are gonna get mixed up, you know, because you have to. So if you put, if you put x here and put y here,
Yeah.
eh?
Yeah.
Yes.
Yeah, man. Yeah.
Yes, but you see, let me say traditionally, conventionally, them do it this way. You would have to go down and remember, so this is your x. So let's do it. Let's do this. So this was your x and this was your y, right? So you would be so
the values down here now. So the values, right? You have to scroll to get the values. The values them to the left. Q, 3, -1 and 2 to your left.
-1.
No, I'm just saying you have to scroll back up to the coordinates for the Q. For the right to the left.
Right. Stick with this, young man.
Yeah, man, that's all right, man.
Yeah, mix
sir. Sir. Sorry for the noise. Is the background. Is it -y? I didn't hear it. Was it -y as you said?
Yeah, man. It was 3x minus 1y plus 2z. So,
I was wondering if the y should have gone to the left instead of the right. That's what I was wondering. Sorry about that, sir.
Yeah, man, it gone to the left. Here is your origin, you know. X going this way.
Oh, yes, sir. It's true. All right, sir. Okay.
One,
Yes, sir. I see it, sir. Thanks, sir. I see it.
All right, cool. All right, what we there now? All right. Pretty much, this is what we said already, right? Where we say, well, you know, when we were explaining the box there, and we said the x equals 0, we go back up here. So x equals 0 would be this back plane. So this is just, which is x equal a constant, which is 0. So this is just showing the same thing. So for example, z equal a constant. So z would be equal, say, 2. Z equal 2 plane, right? So it's in the xy plane, but it's z equal a constant. Get that?
Yes, sir.
You get that sort of kind of?
No, I get that one.
You get that? Okay, then. So this is
Y is always equal to 0 at the back plane, sir.
Ask again.
I mean, x is always equal to 0 at the back plane.
Not, let me see. No, if okay.
It would be at the back ends, like it would be at the origin.
No, hold on it. In this case, right? In this case, one of the YZ plane, which is the back plane, right? One of the YZ plane is at x equals 0, and the other one is at x some value of x, right? Say, suppose this second plane was at x equal -2. That would be the back plane. You with me?
Oh, yeah.
So you can't think of it like it always have to be the back plane.
Yeah. In that
Depending
case, the 0 would have been the front plane.
Right. If x was -4, the x equals 0 plane would be the front plane.
Yeah, man, makes
With me?
sense.
Make sense?
Yes, sir. Makes sense, sir.
Okay. No. This is very crucial again. All right. So in the Cartesian coordinate, to reach from the origin to some point out here, you can go x, y, z, right? Along the x, some value. Along the y, some value. In the same way we said earlier, if you so the vector from the origin to your destination would be r. Say r, right? So we would say then r is x unit of unit vector r. With me? Hello?
Come again. Come again.
All right. I'll go back up at this one.
Yes, sir. We are here, you know.
Yeah. You know, and then let me tell you something, man. You know, some other guys know me, you know, and I know some is a sensitive youth, right? And if me not hear when I talk to him, I feel the boy, one of those things.
Real, sir. Real.
Sorry
Sorry about that, sir. Sorry about that, sir. Two one now one come in one time. We know exactly. We normally expect one or two. That's why.
Yeah. I you know, I believe some of the things I'm boring. Mr. Man, we all crying, man. That's why I turn off the video, you know. So, me not have to holler. All right. So, all right. Hold on now. We're going. Your vector Q, right? Go from 0. No, this vector go from 0 to Q, right? You got 3 units in the x direction, negative 1 unit in the y direction, and positive 2 units in the z direction, right? So, let me do that again. So, you have unit vector in the ax. So it would be 3x ax negative 1y ay or 1 negative ay plus 2 z az. So that's how you would write that vector. 3x ax minus y ay are 1 negative ay plus 2 z az. So you have x1. So any point on the x-axis having coordinate x1, 0, 0. So x1, 0, 0 would be going this way. Right? So it's x1 in the ax. All right. Any question on the Cartesian vector system? Take that as a no.
No, sir.
No, sir.
All right. This is very, very.
Sir, the session is being recorded that we can go back to it as reference for reference.
Yes.
Also, it will be sent to the emails.
Yes, it will be sent to your group email.
Okay then.
All right. No. Oh boy. I wish I had that slide. I'm going to take it that you guys know how to differentiate, all right? You guys can differentiate?
Yes, sir.
Yes, sir.
dy by dx of x squared give you what?
2x. 2x.
2x.
Eh?
2x.
dy by dx or dx squared dx equal 2x, right?
Yes, sir.
How you come by that?
Multiply by constant and minus
1 from the power.
1 from the power.
Well, how then come by that?
Well, I guess it's a whole gradient thing.
Hmm?
It's a whole gradient thing, you know.
You have a piece of paper?
Yeah, man.
All right. Draw xy. One axis is x and the other is y. You do that?
Yeah, man.
Yes, sir.
Yes, sir.
Make up a little table now. One side is x and one is y. X equals 0. What is y? Y equal x squared, right?
What do you want? Y equal x squared.
So x equals 0. What is y?
0.
X equal 1. What is y?
1.
X equal 2. What is y?
4.
4.
X equal 3.
That's 9.
Plot a little graph now on that thing when you make up. So you would have 1 point is 0, 0. The other point is 0, 1. The other point is 2, 4. And the other point would be 3, 9, right? Right?
Yeah, man.
Yes, sir.
Yes, sir. You have it, sir.
All right. You're gonna draw that graph. You draw the graph?
Yes, sir.
No. You're gonna find the gradient at any point on the graph. How do you do that?
Draw a straight line and draw a tangent.
You draw a straight line. You draw a tangent at the point, right?
Yeah.
Yes, sir.
Yes, sir.
And you go on to do the rise over the run, right?
Yeah.
So you end up with a little triangle, right?
Mm.
Yeah?
Yes, sir.
So that little triangle now, we are going to call the one along the x, dx.
Mm.
And the one along the y, dy. So the gradient at that point is dy over dx. Now, the point, let us label that point x, right? And the deviation from x along the y is your dy. And the deviation from z, no, the deviation along the y, that is, you would call it the vertical side of your triangle, would be dy. And the horizontal side of your triangle would be dx. Now let's go back to the formula. Y equal x squared. So you deviate, let's use the delta sign instead of the dy for a minute. So you deviate delta y from the point. So let's say y plus delta y. That would be equal to x plus delta x all square, right? You following me?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Let me know now because the rain falling and I want to make little noise. So I want to know you're hearing me clearly.
Sir, what you're explaining, is it on the screen?
No, man. I said I don't have a slide for this. So that's why I tell you was to draw it. Did you
Pure
draw
turn
it?
down rain back that side, you know, sir.
Hmm?
Pure turn down rain back that side, you say, no. When that happens, the light soon go. The thunder always look out the light and then the internet go.
Yeah. So, but so far you're good though, because me good so far.
Yeah, man, for now.
Mm-hmm.
So the last
So we go
the
back to week. Eh?
I was the last thing you said was y plus delta y equal delta x plus x squared.
Yeah, so x plus delta x in a bracket square, right?
Or x plus delta x squared.
So you have y plus delta y would be equal to what? X squared plus 2x delta x plus delta x squared. So y plus delta y equal x squared plus 2x delta x plus delta x squared, right?
Yes, sir. I have that, sir.
You with me?
Yes, sir.
Yes, sir.
Everybody with me? If anybody not with me, talk up in a virgin or sister or whatever.
Trying to follow.
Okay.
Sorry, hold on. You said look, I get the y plus delta y equal x plus delta x all squared.
Yes. Remember we start y equal x squared.
Yeah, man.
So since y equal x squared, y plus delta y would be x plus delta x all squared, right?
Okay, okay.
You with me?
Yes, sir.
Yes, sir. Making a little sense, sir.
That makes sense?
Yes,
no.
sir.
No, remember delta x is a small change along x, right?
Yes, sir.
Agree?
Yes, sir.
Yeah.
Yes, sir. All right. So if you have a small number and you square it, what you get? If you have 0.01 and you square it, what you get?
You get a small.
They get a small number, sir.
You get a very, very small number. So the smaller you make delta x. That almost go to 0, right?
Okay.
Eh?
Yes, sir.
Yes, sir.
If you make delta x very small and you square it, that's almost 0. So,
Yeah.
Yes, sir.
all right. So cross out delta x square and say that gone to 0. Okay, you're gonna make delta x very small. So you are left now with y plus delta y equal x squared plus 2x delta x. Everybody get that?
Yes, sir. Yeah.
Yeah, which further?
But what we start out with, we say y equal y equal x squared, right?
Yes, sir.
So y cancel x squared.
On both sides.
Yeah. So we are left now with delta y equal 2x delta x, right?
Yeah.
Yes. Yes,
Yes,
sir.
sir.
So delta y over delta x equal what?
Times x.
2x.
Equal 2x. So you get n times x to the n minus 1.
Okay.
In.
I can repeat the last sentence, sir.
That's how you get dy by dx of y equal x squared becomes n times, where n is 2, it becomes n times x to the n minus 1.
Oh, yes, sir. I got that, sir.
Remember when I asked you how you get dy by dx of x squared, and you say it's n times x to the n minus 1? That's how they come up with that relationship.
Mm.
All right, sir.
You with me?
Yes, sir.
Yes, sir.
Sure, some mangaroo never teach you know that. That's your sir mangaroo, yes, sir. Get with that. All right. No. So if we have a vector, right? If we have a vector L going from 0 to a point P, so you go along the X for some number of unit vectors, then you go along the Y for some number, a unit vector, then you go along the Z for some number, a unit vector. You agree with that so far?
Yes, sir.
So the differential vector now would be dx along the ax plus dy along the ay plus dz along the az. Tell me, say I don't get that. Who don't get that? Who don't get that? Put up their hand.
Holy band gone.
What if a hand gone up?
You know, see them?
Yes, sir. Repeat that. Repeat that.
Repeat that. Okay. Vector L.
Yes.
Go from 0 to some point in space, P, rotted. How about that? One day me have no lightning rod by my foot.
Guys, you listen.
Eh?
Guys, you let them man lighting up there.
No, I'm there. You know, man, develop proper.
Yeah. Worse, I lightning place up there.
Wait, give me a minute. I'm going to plug out and something. Hold on, let me know. Let me mash up. Hold on. Give me 1 minute.
Yo.
But sure.
Wait.
Why sound like now lick back the side up? It look like a thunderstorm or lightning storm, one of them, but I will it.
Myself, if I say I will if
I love the rain because the country well wants some rain.
So
But
hold on,
lightning and thunder start lick. You know, you can't start times.
so we're able to get the recording?
Eh?
Yeah, man, him said that. Him said I'll get it.
Okay, no problem.
All right. Back with you. Let me do again. So we have a vector, right? From the origin to some point in space. All right? Call it point P. So to get from 0 to point P, you travel along the x-axis. All right. Say point P. Get your paper. Say point P is at 3, 2, 4, right? Point P is at what?
3, 2, 4.
3, 2, 4.
3, 2, 4, right? So you would have something like this, like right here. You see where I have the arrow? P,
Yes, sir.
P, bracket 3, 2, 4, right?
Yes, sir.
X, Y, Z. You with me?
Yeah, man.
So that means to go from the origin to point P, you travel 3 along the X, 2 along the Y, and 4 along the Z. So P would be at some point here, yeah? Say something, no, man.
Yes, sir.
Yes, sir.
Yes,
Got
yes,
that.
sir, yes, sir.
All right. So your vector, you go 3, 2, 4. So your vector would be from 0 to P. Your vector L.
Yes, sir.
Yeah?
Yeah, man.
Yes, sir, I get
So now, and we say a differential length. That means a small change from any point along your vector. So DL, vector DL would be a small change in L, which is our DL, vector along the L. Yeah? So DL would be a small change. Remember, L would be X, AX plus Y, AY plus Z, AZ, or 3AX, 3X, AX plus 2Y, AY plus 4Z, AZ, right? So your differential L would be a small change in your X, small change in your Y, small change in your Z. So along your L, your vector L, a small change in L would be your DL. That's all this is saying. So dy dx is the differential length in X. dy is the differential length in Y. And dz would be your differential length in Z.
Not now again, then what time for 3 o'clock, then at 2:30 now, then what makes sense?
Eh?
Sorry, sir, not you.
Did I say something?
No, sir, no, it's okay.
Okay. So that is that. Okay then. Going back up. Yeah.
This document that they're teaching us from, we have access to it, sir?
You know what? I don't know. I go ask Jay later if he can, because it's in a PDF. I don't know what to do with it.
Can email to us, sir. Jerry started it out, sir. Let's start with Jerry. Right, Jerry?
Yeah, Jerry started it out for me.
Yeah.
All right.
I think him did send it already. May I check still?
What I have to do is send the link. Because I feel what I'm a professor. And then him allow me to use it. So since we never have my PowerPoints them already. But yes, man. I guess you will get it somehow or the other. All right?
Okay, sir.
All right, sir, cool.
Yes, sir.
No. All right. Go back to this one alone. Anyone on the system. Vector O to P, right? Would be this length here. Now the 3-coordinate system, this length O to P would be it would be the square root of x squared plus y squared plus z squared would give you this, right? Remember that?
So that's the magnitude.
Magnitude of this vector would be x squared, the square root of x squared plus y squared plus z squared, right?
Yeah.
Yes, sir.
Similarly, the magnitude of the L would be the square root of the x squared plus dy squared plus dz squared. Now, here why these are important. Here why these are important. If you notice, we talk about This course is about vectors, right? So we talk about addition, subtraction, scaling of vectors. Now, here what's gonna happen now, or shortly, in about 2 weeks' time, right? We are going to say that we have a point charge at P, X1, Y1, Z1, right?
Mm-hmm.
Yes, sir.
So that's a vector. And we're going to say we have a point charge P1 at this. And we're going to say we have another point charge P2 at some point here, X2, Y2, and Z2, right? And we are going, so you have a charge, so you're going to have an electric field, right?
Yes,
So you're going to want to find the electric field at some other point P3 out here. You with me?
Yeah.
Yes, sir.
Similarly, you're going to say you have a sheet charge in the X equals 0 plane. So it's going to be on this back wall here, right? So it's in the X equals 0 plane. So you're going to have a charge going from in the Y, going from infinity to negative infinity, and from infinity in the Z to negative infinity in the minus Z, right? And Z X equals 0. So that will become known to you as a sheet of charge. So here we say we have a point charge and another point charge, and we want to find the effect of that charge at some point out here. How is that important in life? Then I say charge give you cancer and all that sitting. So you want to know, say, when they put up the cell tower here, and you have an next cell tower here, and you live there, so what kind of radiation you're getting? You with me?
Yes, sir.
Or if you have a sheet of charge there, so, and one out there, so, or you have a sheet here, and you have a point here and a point there, how you add all of these charges to come up with your net effect here.
Okay.
Or if I can get one of the joke I'm get on the WhatsApp with this coronavirus. Then I say 5G give you coronavirus. So what right? I know if you have because when you say 5G, you're talking about the frequency, and that have an effect on how far from the source it can go. So if the source is your cell phone or whatever, what kind of effect you have in your jawbone, and whether you get coronavirus or not. So you have point charge, you have sheet charge, and which will be important to us. And we have what we call a volume charge, right? So the volume of this box, which is in the Cartesian coordinate, is the length x times y times z, right?
Yes, sir.
Yes, sir.
You hear me? So in a similar way, with the line charge or the line vector, where your differential length is dx ax plus dy ay plus dz az, your and your magnitude is this. For the volume charge, your volume is x times y times z, and your differential volume is dx times dy times dz. And for your surface or sheet charge, your differential surface, because how you go? Okay, I guess. Well, it's here. So you imagine you're dealing with a surface here on the back plate, right? On the back side, right? It's a vector. So your surface here is a vector. So
Yeah, David.
in the same way, where you have your line is in, your line going here would be L in the AL direction, right?
Yes.
Which would be X, AX plus Y, AY plus Z, AZ. That would be L, AL. If your surface is in the ZY plane, the vector would be a line normal to the plane. So it would be at right angle to the XY plane. So what direction would that be in? In the AX. This is your plane. Your plane is XY. Your normal is AX. So your surface vector would be ds, which is d in the XY plane, in a direction normal to the plane.
Sir, can I ask a question, sir?
Yeah.
All right. I know you just explained about the point charge, the sheet, and the volume charge. But I want to know, in terms of the point charge, is it the same as the line charge, sir?
No, man.
No. Good.
No.
So
your point charge is a point, is where it's a point.
Good.
But the direction of your point charge would be the direction from the origin. Now come on for this, man. All right. What time is it? 2:50? We'll pick up from there. Remember your question, because it's like then I get serious.
All right, sir.
So we'll pick up, which page, man? Page 15. All right, so we pick up from there on Tuesday, okay?
No problem, sir.
All right, sir.
All right, sir. No problem.
All right, sir. Take care.
Have a good weekend. Dre.
Yeah.
Dre.